Alright, so this video will be one of three that covers different topics that are covered in section 2, or sorry, section 3. Section 3 is really going to be the heart of this chapter. We're going to do other things with other parts of it, but this is going to be the majority. Between 7.2 and 7.3, this is going to be one of the things that you'll see more questions about on the AP exam than anything else necessarily specifically in chapter 7. Now you're going to see some applications where you're going to have to do stuff from section 1, but as far as obviously this is a topic that we covered in a certain section, it will be 7.2 and 7.3. There's almost always a free response question that has to do with 7.2 and 7.3. I think there's only been 1 year in all the years that I've taught AP Calculus so far, and right now that's about 8 or 9 that they did not have a free response question. So most of the time they do. So let's go ahead and get into it. Find the volume of the pyramid. This is volume by slicing. I talked about everything other than that on the title page. But what we're going to do is we're going to find the volume of things by slicing through them, finding the area times the thickness, which gives volume, and then integrating. And that's going to add up all the different parts. Now we're going to start off with a very simple example. Now we're going to make the volume of this pyramid way more complicated than it normally would be. But more than anything, I want you to see how we're doing it. I'm never going to ask you to find the volume of a pyramid using this method. I just want a figure that you're familiar with for you to actually see how it would be done. Alright, so if we were to find the volume of the pyramid, we want to consider a horizontal slice through the pyramid. So if we go and we cut right through there, the volume of the slice would be S squared dH, where S is the width of the side. Remember, any cross section where we're cutting through this, since the base is a square, that slice would also be a square. So what we're doing is we're essentially doing this number. We're taking and we're cutting a slice out of this thing, and imagine that that's kind of shaded a little bit. That is a slice that's parallel to the base. Doesn't look like it because I've drawn this side a little bigger, but anyway, you get the idea. So the volume of the slice is going to be S squared times dH, where dH is the thickness that we're talking about down here. And what is S squared? Well, that is the area of this cross-sectional slice. So that's the way we're going to set it up. So I want you to go ahead and start thinking about that, area times thickness, because that's the way we're going to set most all of these up. So if the volume of the slice is S squared dH, if we put a 0 at the top of the pyramid and make down the positive direction, then S is equal to the height measured from the top down. So we can actually flip the axis over in this case and get something that's actually going to be helpful for us with integration. Now we could also start with 3 with 0 at the bottom and go up, but we would end up doing something like 3 minus x or something with our integration, our upper and lower bounds. So the volume of the slice is H squared dH, which means that the overall volume of the entire thing is the integral from 0 to 3 of H squared dH. Now if we do that integral right there, we get 1/3 H cubed And when we integrate from 0 to 3, or evaluate from 0 to 3, it's going to be 9. Now, this correlates with the formula. V equals 1/3 B, capital B, area of the base, times the height, which is 1/3 9 times 3, which would also be 9, because the 1/3 and the 3 would cancel out. Now, the reason we end up with h cubed here is because this length and this length, this length and this length right here, this length right here, and that length over there, or this length over here, were all the same. Like I said, don't worry so much about this. Just understand how we're taking our slice, finding the area of that slice, and then integrating. Or sorry, the volume of the slice. It's the area times the thickness. All right, so for the method of slicing, you want to sketch the solid and a typical cross section. Most of the time, they're going to tell you what kind of shape it's going to be. We're going to do an example here in just a little bit where they tell you it's a square. But you're going to sketch the solid in a typical cross section. More often than not, what I usually do is I'll just sketch the plane, the figure that I'm integrating across, and one cross section. I don't try to sketch the solid because, well, you guys have seen my drawings. My drawings are horrible. Number 2, find a formula for V of x. Note that I used V of x instead of A of x. You're going to find V of x by doing A of x times whatever the thickness is, which in this case, if you're finding area with respect to x, it's going to be A of x times dx. That's the volume. Area times the thickness gives you the volume. Number 3, find the limits of integration. And then 4, integrate V of x to find the volume. So let's do an example. A 45-degree wedge is cut from a cylinder of radius 3 as shown. So we're cutting that slice right there out. This is what we're finding the volume of. Find the volume of the wedge. Now, you could slice this wedge several different ways, but the simplest cross section is a rectangle. And it's a rectangle sliced right across there. Now, what we need to think about is a couple of things. We need to think about the fact that we have the equation of a circle, just like that. So over here on this, that's your x, and this is your y. So keep those in mind as we're going through this. It'll help you to understand things. So now, as x gets further away, notice the thickness of this thing is going to be dx. So we know we're going to have dx, and we need to find the area of this with respect to x. Now, if we let h equal the height of the slice, then the volume of the slice is V of x equals 2yh dx. Now, the reason we can say that this right here is also x, sorry, never mind, we're not there yet. So this is the height, and how did we get 2y? Well, if you remember, we're defining over here the center of that circle is the origin. Well, if we plug in, and we're going to find an equation in just a second, but that means that we go y in this direction and we go y in this direction. Well, if you add this value plus that value, that's where you get the 2y. And that includes even when you're over here and you've got your cross-section area cut out of it. This is still a y value, this is still a y value. Now we're going to find how to relate that y value to x momentarily. but that's where the 2y comes from. And we're just calling this height right here h. We'll analyze it and get it with respect to x in just a second. All right, now since the wedge is cut at a 45-degree angle, we know that this side and this side must be equal. Therefore, whatever the x is, this number right here, so if this is x, this is h, and this is at a 45-degree angle, that means that these two have to be equal. So h and x are interchangeable. So that automatically allows us to put an x right here. So we're one step closer to having this volume described in terms of x. Now the other way, we have to deal with y. So we're going to have to deal with y, and we're going to use the equation of this circle right here. If we have a circle that's defined as the center of the circle is at the origin, if you remember, the equation will be x squared plus y squared equals r squared. Well, r, it has a radius of 3, so we square that, and we get x squared plus y squared equals 9. Now, you need to solve this thing for y, and that's going to give you this value right here, this value right here in terms of x. Now the thing that's awesome about being with a circle is if you know that value, you also know this value over here because it's the same thing just in the opposite direction. So we end up multiplying this thing by 2 to get that base of that rectangle. So 2 times the value of y is the base of the rectangle, times h, which is the height of the rectangle, times dx, and that's going to give you the volume of this green platform, this green thing right here that actually has a thickness of dx. Now, how will we find the volume of the whole thing? Well, we need to integrate. So we're going to integrate. We're letting x go from 0 to 3. That's where our bounds come from. And we integrate this exactly like it is. We can let u equal 9 minus x squared to use a little u substitution. Then the derivative of that's going to be negative 2x dx. We can move the negative to the other side because we've got our 2x dx. And if we wanted to change our bounds, we could go ahead and do that. Plug in 0, we get 9. Plug in 3, we get 0. And we have a negative that goes all the way out front because of that negative 2 du, or negative du. So we end up with, once we do all our conversions with this integration by parts, or sorry, u substitution thing, we get negative integral from 9 to 0 of u to the 1/2 du. Now, since we've already changed our bounds, we don't have to worry about converting it back to the square root in terms of x. So we can just take the antiderivative, evaluate it from 0 to 9. Notice we got rid of our minus here. That's why these are flipped. Remember, changing the sign, you can just flip your upper and lower bounds. So we get 2/3 u to the 3/2, evaluated from 0 to 9. Means you're going to plug 9 in. 9 cubed over 2, or sorry, the square root of 9 cubed. Well, guys, here's the thing. When you do these, let me give you a little aside here before we get too far, because I want you to make sure you know how to do this, and you can do it by hand if you have to. If we're doing 9 to the 3/2, don't do the power first if this is a perfect square. We're taking the square root here. So take the square root first and then raise that to the 3rd power. It's much easier. So what's the square root of 9? It's 3. And then you take 3 and you cube it. That's where we get 27. Now with the 0, it's easy because 0 to anything is going to be 0. You get 2/3 of 27 minus 2/3 of 0, which is just 2/3 of 27, which is equal to 18. So the area of this thing that actually came from a cylinder is 18, and it doesn't have a pi in it at all. And we never even used pi anywhere in here. All right, now there is a little theorem, and you won't use this, but it's a nice little thing to know because it can simplify a problem that you have to do. You could use it to simplify a problem. It's called Cavalieri's Theorem, and it says that two solids with equal altitudes or heights and identical parallel cross sections have the same volume. So we're looking at a cylinder here. That would be the simple version. But what happens if we have a wavy cylinder? Are the volumes the same? Well, the volumes are the same as long as if they're the same height, which these are, and we have identical parallel cross sections. So for every level of this cylinder, or this curvy cylinder over here, we have exactly the same circle that we would cut out at that level on the other side. As long as those match all the way up and all the way down, then these are going to have the exact same volume. All right, so let's look at a problem. This is more along the lines of what you're actually going to have on my test, on the AP exam, and probably on your homework. It says the solid lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. So that's where we're going with our x's. We're integrating from -1 to 1. The cross sections perpendicular to the x-axis are squares whose sides run from the parabola y equals x squared to the parabola y equals 2 minus x squared. Find its volume. All right, so first things first, you want to find your base. That's the base in the plane. And that's where you're getting the y equals x squared and the y equals 2 minus x squared. Get the xy dealt with first. Get that picture on a graph. You need to sketch it. All right, I went ahead and graphed both of them. Here is my 2 minus x squared, and here is my x squared. Now what you want to do, much like we did with in 7.2, we had to find that slice right there. Well, all that is, it's the upper function minus the lower function. All right, well, what we're going to do here, that thing is going to be, that line right there is going to be one side of this square that we're dealing with. What's going to happen is this. I'm going to go into 3 dimensions here. I'm going to show you exactly what's happening. We're going to have, here are the 2 parabolas. There is y equals 2 minus x squared, and here is y equals x squared, the red down here. And this is the green line right there. And what's going to happen is you're going to have a square come up out of that figure into space. If you're looking at this on a piece of paper, it will be coming up out of the paper at you, which means that if we know what this length is, then we know what this length is, because that's how you find a square. So now what we would do, we would set it up to find the area of the square times the thickness, and we would integrate from our bounds, -1 to 1. So keep this value, this picture right here in mind. Try to sketch it if you can. And then on the next page, next slide, we're actually going to work this thing out. All right, so we have this picture again. There is one side of my square, and here are my 2 functions. So if I know the length of this, or can find the length of this, which I can, the length or the side is going to be 2 minus x squared, that's the upper value of the function, minus the lower value of the function, so x squared. So when we simplify, we have 2 minus 2x squared. That is the length of this green line right here. Now, if you have not put together how we actually find this, here's what happens. For any value of x, and this is true anywhere across here, that's going to be the equation no matter what x is from -1 all the way up to +1, this will find the distance from this graph to that graph. That's what it is. Finds the difference right there. Now, the reason why it can do this is that this value right here is which y value? Well, it's the 2 minus x squared. 2 minus x squared. And then what is this value right here? Well, it is the y equals x squared. So this length right here, if we take it away from this whole length right here, what's the only thing that's left? The length of the green. So we have a function right here, we're calling it s because it's the side of the square, that's going to find the length of this line right here no matter where it is. Now, just a second, and I'm going to show you another three-dimensional figure so you can hopefully kind of see how this works. Alright, so here is the graph. I've put it in another program, and we've got the blue, I don't remember which one of these, I think that's the 2 minus x squared, and the red, which is the y equals x squared. And here's another version of that square. And what's going to happen is this thing's just going to move across. Hold on, let me change to the right variable here. And as x changes and scrolls across this thing, notice what happens. The square, the base gets longer. Well, if it's a true square, this length and this length have to be the same. So this is going to happen as we go all the way across. And we lose a little bit of it there. It won't show for some reason, all of it. But you can still imagine how tall that square is getting. And as we get over here, as that green line shrinks again, my square shrinks again until it goes all the way down to nothing. That's what's happening. And what we're doing when we integrate is we're adding every single one of the volumes that we get from those little bitty slices that are squares. That's where all this information is coming from, and that's what we're doing. Alright, so let's go back. So we know how to find the green line now, hopefully. We know what we're doing. So let's put together our volume. What is v of x? Well, v of x is going to be that square times the thickness. Well, how do you find the area of a square? Remember, v of x is nothing more than the area of the cross-section times dx or dy, depending on which way your slice goes. In this case, we're doing it with dx. So we know we need a function of area that's in terms of x. Well, what is the area of the square? Well, it's just the side squared. Well, what is the side? The side is the green line. What did we just find? We found that s is this thing. So this is s squared dx. And we can go even further and express that area in terms of x by saying it's 2 minus 2x squared quantity squared times dx. So that's the volume of one slice. So how do we find the volume of the whole thing? Well, let's move over here because this is going to be a little bit of work. So actual volume is going to be the integral from the intersection point here to the intersection point there. So from -1 to 1 of 2 minus 2x squared quantity squared dx. Now, do not go in here and say that that is 4 minus 4x to the 4th. Remember, you have to, if you're squaring a binomial, you have to FOIL it. So what we're going to do is we're going to end up with the integral from -1 to 1 of 4 minus this times that and double it, so minus 8x squared, and then square this last one, plus 4x to the 4th dx. Alright, so at that point, all you have to do is integrate this. And guys, the integration of this is not that difficult because what we just integrated term by term. So what do we end up with? Well, we end up with integral of 4 is 4x. Integral of 8x squared, we're going to increase that by 1 and divide by it. So it's going to be minus 8 thirds, x to the third. Antiderivative of this, you're going to increase that and divide by it. So it's going to be plus 4 fifths, x to the fifth. And we're evaluating that from negative 1 to 1. Now, I'm going to tell you something. The biggest problem you're going to have with these, because it's always the biggest problem that students have with these, is the last part. You're not going to have, the setup is going to be a problem. We'll hopefully get most of those ironed out, but these fractions are going to give you fits. Just because, well, I know how you guys love fractions. So let's go ahead and plug in the 1. So we're going to end up with 4. 1 cubed is 1, so we end up with minus 8 thirds. 1 to the fifth is 1, so we end up with plus 4 fifths. Then we subtract, evaluating at the lower bound. Now when we plug in a negative, each one of these powers is odd, so what is it going to do? It's just going to change the sign of the same thing we had here. So we get negative 4. 4 times negative 1, negative 4. Negative 1 cubed gives me a negative 1. Negative 8 thirds times negative 1 gives me a plus 8 thirds. And then 4 fifths times 5, or negative 5 to the fifth power. Sorry, negative 1 to the fifth power is going to give me a negative 4 fifths. So here's the neat thing. With this case, once you do this one, you've actually found the value of this one. It's just negative or positive, the opposite sign. So we need to do the fractions here. What's a common denominator between 4, 8 thirds, and 4 fifths? Well, it's going to be 15. So you're going to have to change each one of these to 15ths. 4 in terms of 15ths is going to be 60 15ths minus this one is going to be multiplied by 5 top and bottom. So you're going to end up with 40 over 15. And then plus, this one's going to have to be multiplied by 3 top and bottom. So we end up with 12 over 15. So we end up with 60 minus 40, which is 20. 20 plus 12 is going to give you 32 over 15. Well, like I said, since we have the exact same numbers over here, just opposite signs, this one over here is going to be negative 32 over 15. You can go ahead and do that if you want to, but you're going to end up with negative 60 over 15 plus 40 over 15 minus 12 over 15, and you're going to get negative 32 over 15. So you end up with 32 over 15 minus a negative 32 over 15, which gives us what? 64 over 15 for our answer. 64 over 15 is the volume of this thing that would be made from that. All right, now real quick I want to show you what the actual figure, or give you an idea of what the actual figure would look like. So here are our two parabolas and where they intersect. And it's kind of backwards on this. I tried to flip it around, but I really couldn't get it to do it. But there is your solid that you just found the volume of. We can see our squares coming out here. And the further we go across, the bigger those squares are. That's why we have this flat face, or seemingly flat face, that goes across the top. But that's where we get, that's what we get with our solid when we do this. So that's the shape of the solid right there that we just found the volume of. It's almost like it's kind of hard to see sometimes, but it's kind of like a football with flat sides. With one flat side that's just flat, the other one is flat across the top. But that's what it looks like.